Okay, thank you very much for having this paper on the program. Really glad to present this new work joined with Soma at Yale on innovation networks. So innovation is the source of long-run growth. And by its very nature, innovation often requires researchers to build on prior discoveries, sometimes outside of one's own field or expertise. So because of these knowledge spillovers from sector to sectors, innovation allocations in a decentralized world may be inefficient, and that's why how to design effective policy to stimulate growth and innovation has long been a central question in both policy and in economics. So many countries around the world have dedicated government agencies for the design and implementation of innovation policy, and there exists a long history of large literature in economics thinking about innovation policy, mostly from two perspectives: over time dimension and within sector allocation of R&D resources. Meaning, is the economy as a whole allocating too much or too little resources for innovation, or are we giving the most innovative firms the amount of resources? So in this paper, we're going to take a different perspective and analyze the cross-sector allocation of resources in the presence of an innovation network where there are knowledge spillovers across sectors. So here, this is an illustration using US Patent Citation Network, where each node is a fairly aggregated technological class. Links across nodes capture the strength of citation relationship across sectors. So in this talk, we hope to build methodology and some answers to the following type of questions. Looking at this network, how much should an economy allocate R&D resources to pharmaceuticals versus semiconductors? How does the answer depend on the production structure and the network structure? How does the answer change if the economy is exposed to foreign knowledge spillovers? And are some economies allocating resources better than others? Can we quantify that in the data? What are countries actually doing? So that's the type of questions that we will answer, both theoretically and empirically. We start from the theory, where we built a multi-sector quality ladder type endogenous growth model with cross-sector knowledge spillovers. And the structure of these spillovers is what we call an innovation network. So each sector will have a state variable. Think of it as a knowledge stock at the sector level. These knowledge stocks reflect an accumulation of past R&D in a sector. And these knowledge stock in each sector can benefit future R&D, making R&D more efficient in other sectors of the economy, hence a network. So because of knowledge spillovers, decentralized allocation may be inefficient, and a key goal of this paper is to analyze the social optimal allocation of R&D across sectors. Now, in general, it's a hard problem. The economy features a large number of state variables. Each sector is a knowledge stock, and there could potentially exist a rich network structure of dynamic spillovers across sectors. So R&D allocation at any point in time will have future consequences on the subsequent evolution of knowledge in all sectors of the economy. We have a particularly tractable formulation so that the problem has a very simple solution. We have closed form solution for the entire optimal time path of R&D allocation. And the optimal allocation is implementable with very simple R&D policy, sector-specific R&D subsidies. The sufficient statistic or solution has both qualitative and quantitative implications. Qualitatively, we show that...
You have a quality ladder model, so you potentially can have creative destruction there. So you would say some firms could disappear if that you somehow don't look at that. You could have endogenously the kind of things that was discussed in the previous presentation.
Mm-hmm. So that will be in the background when we analyze social optimal allocation. So what matters is really not what happens to firms' decision, but we are going to show you a particularly simple form of decentralized economy to show how these spillovers imply inefficient allocation. But the emphasis will be on the social optimal allocation given the spillover technology, which I will be specific. So qualitatively, we show that planner directs R&D intuitively towards more innovation upstream sectors, sectors that generate lots of spillovers directly or indirectly to other sectors, compared to the decentralized allocation. And a key parameter that dictates where the planner allocates resources, of course the network structure, but also the discount rate of the society. A more patient society should allocate more resources to more innovation central, more fundamental, more upstream sectors. And a more myopic economy should allocate more resources towards goods that can directly benefit the consumer instead of future spillovers. Now we're going to show that this optimal solution also forms a very simple sufficient statistic to compute the welfare cost of R&D misallocation, which I'm going to bring to the data. So that's the theory in the closed economy context. We're going to introduce foreign spillovers, so generalize this to an open economy setting. We're going to show that countries have this incentive to free ride on fundamental technologies across each other, meaning even holding constant the total amount of resources dedicated to R&D as given, an economy exposed to foreign spillovers may choose to behave more myopically and allocate resources in more downstream sectors. So compare Canada versus the US. Both are doing cutting-edge R&D in some sectors, but since Canada benefits so much from knowledge spillovers from the US, especially coming from fundamental technologies, Canada, from a unilateral perspective, doesn't have incentive to reinvent the wheel and build up the fundamental technologies. So planners with a self-contained domestic network, such as the US, are effectively more patient. Planners in a foreign-dependent economy effectively behave more myopically if they optimize from a unilateral perspective. So then we're going to take these insights into the data. First contribution is we're going to construct a gigantic global innovation network based on patent records compiled from more than 20 patent offices, covering innovation from more than 40 countries, about half a century. Using this data, we're going to show some descriptives about how the global innovation network looks and how it has evolved over time. And we're going to do a validation exercise to show that the citation network that we measure do manifest some form of knowledge spillover over the network. And our main application is to apply the theory to measure for each country what is the unilaterally optimal R&D allocation and compare with the actual allocation to assess the cost of misallocation in R&D. Okay? I will build up the empirics and elaborate as we go there. So we're going to start from the theory of a closed economy first. The model setup will only have 2 slides, and the first slide is completely standard on the production side. Second slide will be on the innovation side, where knowledge spillover occurs. So consumer has log intertemporal utility, where consumption at each point in time is a Cobb-Douglas bundle over goods from different sectors. Beta, these consumption shares, captures how important is a sector for a consumer. Sectoral goods are produced from a continuum of intermediates, and intermediates are produced one for one from labor. These intermediates carry quality levels with them, and these quality levels can be improved upon through subsequent R&D. We're going to call the average quality the knowledge stock of a sector, and the collection of knowledge stock across all sectors will form the set of state variables in an economy. And the economy has a stock of workers used only for production, and a stock of scientists used only for R&D, a process which I will describe now. Here's how R&D happens. Sectors employ scientists to do R&D to produce new ideas, and we're going to measure ideas one for one in the data using patents. So at any point in time, the number of ideas generated in a sector depends on how many scientists are employed in the sector. Eta is an exogenous component of innovation productivity, and the key is this object chi, which is an endogenous component of R&D efficiency, which depends on knowledge stock in other sectors of the economy. So chi is the endogenous R&D productivity in sector I, which depends on the knowledge stock accumulated through prior innovation in all other sectors of the economy. The extent to which sector I benefits from sector J, these omega ij's, these elasticities, define the innovation network. So you have the whole matrix of omegas, that's the innovation network.
Are you okay with questions?
Yeah, of course.
You mind just going back for a second to the basic. So now the main on this side, the main endogenous thing is the
state variable.
The QIT.
Yep. So labor worker allocation will also be endogenous, but that would be quite trivial.
I just missed what you said about X. So X is the XIT is the.
So think about, to produce a good in a sector, you need to combine a continuum of intermediates. These intermediates are one for labor. You can substitute it just for labor. Yeah. Okay. So this is the idea production function, and ideas lead to quality improvements following a random Poisson process. So with rate, log ratio of number of ideas per quality, that's the rate at which quality improves. So the growth rate of quality or knowledge stock in a sector is the step size of innovation times the arrival rate, which depends on how many scientists and what is the knowledge stock in other sectors of the economy and so on. That's the model, okay? Now, let's first look at a simple case. Without any cross-sector knowledge spillovers, this omega matrix would just be identity matrix, in which case the law of motion for knowledge stock becomes very simple. You know, the growth rate of knowledge in a sector is log linear in the measure of scientists employed in the sector. In general, it would depend on how advanced is knowledge in that sector relative to other sectors and so on. That's the model. We're going to show you some theoretical results. Before I show you the theory results, let me first derive a testable prediction of this law of motion that we're going to use in the data as a validation exercise. So by equation 2, we can actually write the knowledge stock in a sector as a discounted sum of past patterns. And we can substitute that into equation 1 to get this testable relationship, meaning a sector has more patent output if the sector has more scientists, or if its upstream sectors measured through the innovation network has more patents in the recent past. So,
sorry, so conceptually, so how do you distinguish between innovation which are a bit more fundamental or bigger kind of technological change versus increments which are maybe giving more patents but changing the paradigm? I mean, does it matter? I mean, the data mapping, does it matter?
So here,
you have the same size of innovation each time.
Right. So here, for simplicity, we do not have that consideration. We could think about extensions that have it, but the main focus will be, given there are cross-sector spillovers, how do we allocate across sectors? Whereas what happens within sector, whether some innovations are big, some are small, we abstract that away, just so that the cross-sector stuff becomes tractable.
Yeah, and the spillovers are always from upward, or you can also have spillovers from downstream sectors. I may learn something, from the demand, from whatever. Do you assume a priori the direction of the spillovers?
So omega ij doesn't have to be a triangle matrix. So omega ij can have both I from j and j from I. So by innovation upstream, we're saying sector j is upstream to I if omega ij is large. That's what we mean. But you may have, implicitly behind that question, you may be wondering, what if there are spillovers not captured by omega ij, but by production relationship?
Exactly, and here they're orthogonal. There is no...
Yep, that's orthogonal here. When we go do the data, we're going to show it's not as important as the innovation network. That's why we abstract it away. Okay. So this law of motion is something that we're going to use as a model validation exercise when we go to the data. But let me first show you the theoretical results. Now, the main goal is to analyze social optimal allocation. But before I go there, I want to illustrate why decentralized economy may be inefficient. So we're going to set up a particularly stark decentralized economy. Not saying it's realistic. So here we're going to have innovation only done by entrants. And once you innovate, you operate a monopoly line with some exogenous arrival rate of patent expiration, and you exit the market. In which case, these potential entrants who are doing R&D, they do not internalize any knowledge spillover their innovation activity will have on any subsequent innovation. That's where the source of inefficiency is. So to set it up and to just illustrate the result, we're going to think about the environment exactly as I described. So all producers are infinitesimal. They charge a constant markup that relates to the step size of innovation and so on. In this setup, sectoral profit for each product line that's operating is proportional to the consumer expenditure share in the sector. So is the value of a firm. So we have the following very stark result. In this economy where innovators do not internalize any of the spillovers, the allocation of scientists and allocation of workers are both proportional to this consumer expenditure share beta. Okay? This is just to show when firms ignore cross-sector linkages, R&D allocation is inefficient. And the main goal of this study is to analyze social planner problem. How would the planner allocate resources? The planner's problem is to take the initial stock of knowledge as given, try to allocate the path of workers and scientists across sectors to maximize consumer welfare, where I have substituted the production function as a log linear in sectoral knowledge stock, and sectoral employment, the planner is subject to some resource constraint and the law of motion that captures how knowledge spillover across sector occurs. Okay? That law of motion defines the network. Now, this is a planning problem with many state variables and dynamic spillovers, but because of the various places where we have introduced log linearity, the problem has a closed form solution that's highly interpretable. The optimal allocation of resources is time invariant. Workers are allocated according to the consumption share. Scientists are allocated differently. Scientists are allocated according to what we call gamma. Gamma is a vector that sums to 1, and in proportional terms, it's the product between the consumer share and the Leontief inverse of a discounted version of the innovation network matrix. What is the intuition? Well, when we can write the Leontief inverse in the power series form. So the planner, when choosing where to place scientists, it understands that if we place scientists in the sector, it's going to improve product quality, benefiting the consumer. The planner also thinks about, well, if we build up knowledge stock in various sectors, it's going to benefit subsequent R&D that benefit the consumer, and second round and third round and so on. These future benefits are discounted because innovation is a flow activity. Innovation, it's not the employment of scientists today that benefit scientist productivity today in other sectors. It's the knowledge buildup through the gradual process of innovation that benefits subsequent R&D. That's why these network effects are discounted. And the relevant discount rate is the discount factor of the consumer relative to the step size of innovation. When step size is large, these future benefits accrue quickly. Okay? You can already see here that if we assume the social planner is myopic, so take the discount rate to infinity, then the social optimal allocation coincides with the decentralized allocation because the planner doesn't think about these spillovers at all. But in general, the planner would think about these network effects. So to take an example, think about a technological chain with knowledge in engineering may benefit knowledge in semiconductor, may benefit consumer electronics. A more patient society should allocate more resources in R&D in engineering, and a more myopic society should allocate more into consumer electronics. Okay? I'm talking about patience here because when we go to urban economy, as I will show, for an economy that benefits from foreign spillovers, the planner would choose R&D as if it's more impatient. So Canada should allocate more resources towards electronics, and endogenously from a unilateral perspective, US should allocate more resources in electrical engineering in a global equilibrium. Okay. I'll say a few more words about this and about this particular result. One is the optimal allocation is very easily implemented using sector-specific R&D subsidies. Second, going back to the conversation with Philippe, the results generalize with production networks. So what I've been calling the consumer expenditure share, you can think of that as reflecting sectoral value added in a Cobb-Douglas production network economy. And third, this result where the allocation of resources, the optimal allocation is global, is true along the entire transition path, that requires a lot of log linearity introduced here, Cobb-Douglas and log and so on. Well, we can relax many of those functional form assumptions. The precise form of the result still holds along a balanced growth path, meaning along a balanced growth path, if the economy is optimizing, the allocation of scientists should follow in proportional terms to exact the same expression, except now the betas and omegas should correspond to local elasticities. Elasticity of consumption with respect to sectoral knowledge stock, or elasticity of innovation efficiency in one sector with respect to knowledge in another. So what's the implication of R&D allocation on growth and welfare? That's what these next few slides are about. We're going to define an object, innovation centrality, which is the eigenvector centrality, or the dominant left eigenvector of the innovation network matrix. Turns out that this eigenvector centrality is a sufficient statistic for the growth rate of the economy along a balanced growth path. So the growth rate of the economy is affine in the inner product between the centrality vector and log allocation share vector for the scientist. So if you want to reshuffle scientists across sectors, use this formula, you can calculate what's the effect of that on the balanced growth path growth rate. Now, if you stare at this relationship and think about how do we maximize growth by choosing where to place scientists, you get a corollary that the innovation centrality vector is also the vector of R&D allocation that maximizes growth rate. Okay? That's not what the social planner would want. Social planner doesn't always maximize growth. So it turns out that optimal R&D by the social planner can always be written as a weighted average in the vector sense between the decentralized, or what captures consumer surplus, and what captures growth. So planner is always trading off between consumer gain and growth rate of the economy. And the weights relate precisely to the discount rate of the society.
So you give, I guess your previous formula was like Banasich centrality, which is if you ran the discount factor up to some limit where it puts all the weight in the tail.
Exactly.
I see. So that guy will look like the growth rate.
Yeah. So exactly the next point. A myopic planner allocates resources according to the consumer preferences. An infinitely patient planner allocates to maximize growth rate. Okay. Finally, what's the welfare cost of misallocation? Turns out that, if we, for some allocation vector B, we want to compare, for the consumer, one option is to switch to optimal allocation of R&D. The other option is to stay on the current allocation, but multiply consumption at every point in time by a factor. That factor is L, such that consumer is indifferent. So this is the welfare loss from R&D misallocation. It's the inner product, or it's related to the inner product between the optimal allocation and the log distance between optimal and the proposed allocation. Okay, so this is a formula that we can take to the data, at least for closed economies, to assess welfare cost of R&D misallocation. Okay, now let's extend it to an open economy case with international knowledge spillovers. Given the time constraint, I will be a little bit hand-wavy here on the exact environment, and I will just tell you the main intuition of the result so that we can go to the data. So we're going to open up the economy in two ways. So the economy may benefit from foreign spillovers. So the R&D efficiency in sector I depends not only on the collection of domestic knowledge stock in sector J's, but also depends on the collection of potentially an aggregator of all the foreign knowledge that could benefit the domestic economy. So Fij is that aggregator. We're going to model international trade in a very reduced form way. One can microfound it with richer models, but essentially we're going to impose it as a constraint in a planner problem. So the planner will have a constraint that says the vector of imports and exports given the foreign technologies has to be equal to 0. So what is the objective? The planner will choose allocation in a domestic economy subject to this trade constraint, take the foreign knowledge sequence as given, and maximize domestic welfare. And the key qualitative result is for a country reliant on foreign knowledge, meaning the role in this aggregator, the foreign knowledge plays a big role, then its planner will choose R&D as if it's impatient along a balanced growth path. Implying countries with a self-contained network, they should invest more in innovation central sectors. Countries with more foreign reliant network, they should optimally, from a unilateral perspective, invest in more downstream.
You were saying again where you were taking this constraint, international trade as a constraint, given the unilateral problem?
Mostly for simplicity. We could impose a richer international trade model at the background. The qualitative and in some cases quantitative conclusions will be exactly the same. So many trade models, you can map it from a domestic perspective, you can map it into a constraint like that. So you can have, customer dollars and Comanche, calendar payroll at the background from a unilateral perspective that will manifest itself in a constraint because this foreign technology can reflect the collection of foreign productivities and trade costs and so on. Okay. Yep.
I don't understand this result because you still know that if your foreigner learns, eventually there's feedback to you, or
no, because we are taking the foreign knowledge sequence as given. That simplifies stuff a lot. Yeah.
And I also thought, do you take into account that it's going to be good for your consumers? They'll get lower prices? Or
yes, that you do. So you take the foreign knowledge as given, a sequence of foreign knowledge, and you're doing R&D to improve your own knowledge. You don't think about how you would change other country's knowledge stock. But your R&D will benefit your consumer and may benefit through trade. By producing more export, you're going to generate more import.
Yeah, you don't take into account also that if the foreigners learn from you and sell more cheaply to you.
Right, that's not good.
For example, if you look at, I don't know if China is the case, an illustrative case, maybe you start, as you catch up technologically, with more innovative countries. I mean, maybe initially you go into more downstream sectors, and over time you go more and more. There is kind of learning, you see what I mean, and you go more into upstream R&D. Is that something that you could, a dynamic version of your model could account for?
That's implicitly in here because this aggregator depends on the relative level of knowledge stock and so on. But the optimal solution I'm going to characterize only hold along a balanced growth path. Otherwise, it would depend on a full-fledged model, which one could specify, wouldn't have the simple formulas. One can also impose sufficient assumption to assume away these transitional forces. That's actually where we're going to go to take it to data to compute well.
It's not an infant industry, but it's kind of infant industry adapted to knowledge. Do I want to do something very downstream, or I want to build up a bit more upstream, so that then I'm less dependent later on? Is that,
yeah, so that is not here in the sense that the model accommodates it, but the characterization only holds along a balanced growth path. So we're going to define these objects, xij. You can think of it as the share of domestic contribution when we're calculating spillover from one sector to another. When we calculate spillover from j to I, what fraction of that contribution comes from domestic? We're going to proxy it by domestic citation shares. Well, it turns out that the optimal allocation is a vector times the discounted version of the Leontief inverse, where this is a Hadamard product. So imagine this domestic contribution x is just a constant that's common across all sector pairs. Then the domestic optimal allocation is the matrix part is just a small x scalar, and x is the more open, the more foreign dependent a country is in its R&D, the lower x will be. So the optimal allocation is as if the country has very high discount rate. Okay, what is this phi object? Phi in reduced form is the elasticity of domestic consumption in that optimal equilibrium with respect to a marginal change in the knowledge stock in a sector. So that object you can always compute given whatever trade model you have in the background, or in this case we impose a constraint to model for trade. This object accounts for all the general equilibrium in terms of trade effect. Well, in this economy, if planner can actually choose where to allocate sectoral production workers, phi will coincide with sectoral employment share. If the country is in trade autarky, it will coincide with employment share. In general, this is still approximately true. That is equal to the employment share, just because trade effects doesn't really affect this decision too much. So whatever quantitative trade model you impose, it's going to be very close to, with realistic parameters, it's going to be very close to sectoral employment. Okay.
And before we talk about knowledge and network and production, but we know that trade generates knowledge spillovers.
Right.
So that's something that maybe for an extension of the paper, but you could imagine that would be a nice way to link the two. And using data that we have about.
Yep. So that also relates to an earlier comment about, maybe if you buy from your supplier who is more knowledgeable, just in the input-output relationship. We have this empirical test of knowledge spillover through these relationships. We show that even though input-output and trade relationship do seem to infer spillovers, once you control for the citation network, those effects are gone. That's why we don't have it here. But yeah, one could imagine embedding that as well. So let's go to the data. We're going to measure at the sector to sector level the innovation network based on citation shares, and we're going to have US data, but the key empirical contribution is to compile patent data from more than 20 patent offices covering about half a century, 42 countries, most innovation around the globe. So GDP share, we capture about 90% of world GDP share. It's positively selected on innovation, so more than that. When the same invention is filed in multiple patent offices, we unwind to the underlying unique invention and we trace back the original country and sectors. We augment this innovation network with production side information to run our sufficient statistics. Okay, let me show you some descriptors first. On the right, we're listing the biggest sectors in biggest technological classes in terms of the centrality. These are the sectors that should have the most resources to maximize growth. What are these? Well, data processing, semiconductor devices, pharmaceutical technologies, and so on. The figures on the left, I'm showing you log innovation centrality sorting sectors. So there are 645 patent classifications at this level of aggregation. So 10 sectors only occupy the minuscule part of this spectrum. and the y-axis is in logs, just showing that to maximize growth, the allocation of innovation resources will be highly skewed. A visualization of the network at the sector-to-sector level and at the country-to-country level. At a sector-to-sector level, you have a few initial sectors getting cited by everyone else, so the network is highly asymmetric. And at the country-to-country level, there are two salient facts. One is Japan is as large as the US. Japan has as many, if not more, patents as the US. Number two, US is a big knowledge exporter. Japan is fairly isolated, doesn't export knowledge and doesn't import knowledge. Okay. This figure is meant to illustrate how foreign dependent a country is. So for each, whenever a patent cites other patents, we calculate what fraction of those citations are towards domestic patents, and we plot the distribution across industries for each country and year for 3 time periods. You can see that US cites about 80-85% of citations are towards domestic patents. Everywhere around the world, except for Japan, domestic citation share is significantly below 50%. Every country is foreign dependent, and in particular on the US. Japan is an outlier. In 2010, it's citing 90% itself, so Japan is fairly isolated from the rest. And for the fast-growing East Asian economies, Japan, China, South Korea, you can see that they become more and more self-sufficient in innovation. Now, I want to lastly mention a piece of descriptive statistic. That is, the network structure at the sector-to-sector level is highly correlated across countries, highly stable over time, but the optimal allocation of innovation is highly heterogeneous across countries, both because of differences in employment structure and differences in foreign dependence.
Do you control for the quality of the patents? If you restrict three-leaded patents, for example, do you get the same thing?
Yeah, we can try to.
In Japan, there are many patents which are not
yep.
great. Yeah.
So we can measure quality using citations. In the case of US, we measure quality using stock market reaction and value. Yeah. Basically, all patents are qualitative robust. And of course, the model has basically only one parameter, the ratio between rho and lambda. So results I'm going to show you depend on that parameter, but not qualitatively. So qualitatively, all the results I'm going to show will remain true for reasonable parameter ranges. So we're just going to pick some baseline values. Okay. How much time do I have?
6 minutes.
Okay. So we do a validation exercise, which I'm going to largely skip out describing words.
No.
And
we started, no, it's not true. We started 5 minutes late, so you
okay.
have
Nice.
10.
Okay. Validation exercise and then application. Okay. What is the validation exercise? The model predicts that the focal sector, so if this is the network, the model predicts that whenever, focal sector's innovation depends on how many scientists are employed in the sector, and if the upstream sector has more patents in the recent past because more manifest as more knowledge stock, focal sectors will have more patent output. Okay? So we're going to show that precisely in data. So we create, for each sector I, we create an upstream knowledge aggregator based on the network and show that this upstream aggregator predicts focal sector innovation. Now that's a very endogenous regression network. We're regressing my patent on my neighbor's patent in the past. So serially correlated common shocks, a reflection problem, could generate the same pattern. To help rule that out, we have 2 strategies. One is we create a placebo test to show that downstream knowledge doesn't help focal, only upstream helps focal empirically. Number 2, we follow Bloom, Schinkelman, Van Rieden to create a time-varying instrument at the sector level for R&D. So we use sectoral state-level variation in tax and R&D subsidies, or country-level variation in subsidies, and the differential exposure of sectors to location in order to generate time-varying R&D incentive at the sector level as the instrument to show that this relationship still holds. Upstream predicts focal innovation, downstream doesn't. Same pattern holds both domestic and international network. And if we construct a similar aggregator using the input-output relationship, as I mentioned, that predicts focal sector innovation, but not once we control for the innovation networks. So let me go to the main application. We're going to use the model to construct these sufficient statistics and assess R&D allocation across countries. First, as an illustration, okay? Remember, optimal R&D allocation could differ across countries both because of production structure and because of foreign dependence. I want to hold constant production structure and just illustrate how foreign dependence would change the R&D incentive. So here, we're going to compute the red line shows the optimal allocation for the US economy projected on economic sectors, just for the ease of visualization. Once we do pattern classes, there will be way too many sectors to see. So for the US economy, that's the darkest red line. 30% of innovation will be in computer-related sectors, about 8% will be machine and equipment, information services, and so on. And we compute the optimal allocation with a progressively more impatient society that will be isomorphic to the economy is relying more and more on foreign knowledge, but have the same production structure. You see that the allocation allocated to these highly central sectors become lower and lower, and it's picking up more downstream sectors, human health and social work, financial services, rental and leasing, and so on. The same would hold true once we go to the pattern classifications. So for each country M, sector I, year T, we compute the optimal allocation of R&D, and we show that across countries, if we pull across all of them together, sectors that should have more R&D resources do on average get more R&D resources and do have more patent output in terms of number of patents, in terms of citation. In the case of US, you can show it using patent value or the number of inventors allocated to sectors, various measures. These are all highly correlated. Of course, the actual allocation is highly heterogeneous across countries. Some countries allocate it better than others. So in this figure, on the y-axis, we're showing you sectoral share of patents. On the axis is the optimal sectoral share of R&D allocation. Now, the y-axis, we could replace it with sectoral share of inventors, sectoral share of citations, sectoral share of R&D expenditure for a slightly restricted set of countries. Same pattern would hold in that US, Japan, modern-day China, Germany allocate resource pretty well, meaning the line of fit between what's optimal and what's actual is fairly close to the 45-degree line. Economies at the bottom, unfortunately for France, relationship is not very strong. That doesn't imply economies on top have optimal allocation. The allocation are not on the 45-degree line. They are dispersed around the 45, and that accounts for misallocation, which we can use the formula to capture what's the welfare cost. So to zoom in on the US allocation, we're taking the top 50 in terms of patent classifications to look at which sectors are over-allocated versus under-allocated. For the US, too much resources is devoted to lighting devices, apparatus for physical training, signaling and calling systems. On the other end of the spectrum, we have chemical and physical processes, plastic shaping and joining, material separation, and so on. So the model has very rich prediction on how resources should be reallocated across these sectors, and we can compute the welfare cost of that. So I have only shown you formula in a closed economy for how to calculate welfare costs. That is, take some monotone transformation of the inner product between optimal and a log distance between what's optimal and what's in the data. Okay. In open economies, the allocation I showed you only holds along a balanced growth path unless we introduce additional examples to ensure the planning problem is also log linear in the choice variables, in which the formula I showed becomes global. So with those additional assumptions, for example, this aggregator of domestic and foreign knowledge is a coupler-based aggregator, and analogous log linear assumptions in a trade part, we obtain a corresponding result for welfare cost and misallocation in the open economy that's slightly different from the closed economy case. So we're going to define this object C, which is a notion of R&D self-sufficiency. It captures the semi-elasticity, or if we increase the stock of scientists or R&D resources by 1% in the economy, how does the consumer welfare change? How does proportionally consumption change? So in a closed economy with constant returns to scale, this object is equal to 1. In an open economy, depends on how much the economy relies on foreign spillovers, this object will be less than 1. Okay, the more foreign dependent this object is, the smaller is this object C. So the open economy welfare cost of misallocation depends on this R&D self-sufficiency. So the log welfare cost of R&D is exactly the same as the closed economy term, but just multiplied by this scalar. This scalar can be computed using in the data just based on the how much citation that domestic innovation cites foreign countries. So you can already imagine that for US and for Japan, this R&D self-sufficiency term is very close to 1. Many other economies is much smaller. Okay? The more foreign dependent an economy is, given the same amount of misallocation, the welfare cost may be smaller. If all your R&D subsequent R&D only benefits from foreign knowledge, then R&D misallocation in your economy will have very little consequences. Now next I'm going to show you a quantitative result, that is to measure these welfare costs of R&D, which requires me to take a stance on this parameter, rho versus lambda. It turns out that rho over lambda affects both the term directly proportionally, also affects the R&D self-sufficiency, and also affects the optimal allocation. Turns out that this misallocation term is fairly stable. It doesn't change with reasonable variation of rho over lambda, and the welfare costs increase mechanically by rho over lambda, but the R&D self-sufficiency decreasing rho over lambda. So overall, as we change rho over lambda, the quantitative effects are not super large, okay, not a few orders of magnitude different. So if we only account for the misallocation part across countries, you can see that US and Japan have relatively low welfare loss due to misallocation of resources. Other countries have significantly more misallocation term. But when we compute the actual welfare costs, taking into account that US and Japan benefit little from foreign and mostly rely on domestic knowledge spillovers, then the actual welfare loss of US and Japan due to misallocation is not significantly lower than the other economies. Okay. Now, what could explain why some countries have appropriate innovation and other countries don't? Okay. To answer that question, has to be a bit speculative because we are trying to explain the residual of R&D innovation. We're trying to explain all the residual around the 45-degree line in the US economy, for example. We found one observable in the data that seems reasonable. So, I've shown you a decentralized economy where firms are infinitesimal. They don't internalize any knowledge spillover at all. But a lot of innovation are done within innovation hubs, such as IBM, Samsung, Sony, Siemens. They operate in many sectors. They have so many patents in all sectors of the economy, they must partly internalize that if they have a knowledge breakthrough, it's going to benefit their own subsequent innovation. So in some sense, the firm's problem of IBM is analogous to this open economy planner. IBM internalized part of domestic spillovers and think about, take part of the spillover as some other firms as exogenous. So we are working on an extension in the paper to formalize this. So once we incorporate these multi-sector innovation hubs, we're going to show that their solution lies in between what I've been calling the decentralized and the social planner solution. So in the data, if we sort across countries and looking at how concentrated is innovation activities, we see that, so here I'm showing you the fraction of firms that's required to account for half of innovation of patent output in a country. US and Japan, you need about or less than 1% of firms to account for 50% of innovation. On the other end of the spectrum, innovation is significantly decentralized. So according to this theory, US and Japan, you have more of Samsung and Sony and, sorry, not Samsung, but Sony and IBM. They're going to allocate resources closer to the planner solution. So indeed, if we calculate the misallocation component of welfare loss, plotted against this concentration measure of innovation, we see that economies with concentrated innovation activities, they tend to have lower degree of misallocation of resources, a very significant relationship. And we have some direct evidence by looking at how often these firms cite technologies that they also have prior patents. We show that in these economies with better allocation, firms tend to have more internal knowledge coverage ratio building on their own prior discovery. So let me conclude. We provide a theory of thinking about optimal innovation policy and allocation in the presence of an innovation network with knowledge spillovers. We derive sufficient statistics to assess optimal R&D, as well as to do misallocation accounting in closed and open economies. Qualitatively, we show that more patient societies should direct R&D towards more fundamental sectors, and that countries relying on foreign knowledge spillovers do have an incentive to free ride on fundamental technologies. Empirically, we construct a global patent citation network. We use it to validate knowledge spillover dynamics, a part which I didn't get to show today. And we show countries with more innovation hubs, especially US and Japan, they have better R&D allocations. Although welfare cost of R&D allocation is not too much lower in US and Japan relative to other economies because the welfare costs in other economies are mitigated by this foreign reliance on innovation. Okay, that's it. Thank you.